So now we are on to part 3 of springs, and we have gone through the introduction, why we study springs, sofa set plane, how spring works using the principles of momentum and impulse, and we went through the prerequisites, the background information you need to have to understand the equation for springs. And now we are on to part 3. So this is the picture of the shock absorber of the plane. These are wheels, and this is what goes up and down. So let me show you our favorite video again. The plane is landing, 80,000 kilograms of a body coming down at a speed of 90 meters per second. Here it touches and the spring gets squeezed. So it was the natural length, and this has got squeezed. So let me draw a representation of this. So this is my plane almost. And there's one spring here, and there are, and then in the back, and then two here in the back. So the spring in the beginning is in this and let's call it normal length, and then the plane touches, and the body of the plane over here at the point where spring is it touching the spring, so spring gets squished. So the length now is L minus delta L. So the original length was here, and the body of the plane is squished it. So it is L minus delta L. Now imagine that you are the plane. What you will feel. So the plane, and I will not draw the rest of it, the plane will feel a force in the upward direction. And let me call it force by the spring. So you can imagine that suppose there's a block of spring and you push it down, so your hand will feel a force. So you put your hand here and push it down, your hand will feel a force. So the plane of the body of the plane will feel a force, and I call it by the spring. And let me choose a different color for the spring. So first I draw the spring. Now plane, the plane is feeling a force by the spring, and a spring will feel a force in this direction, and this is force by the plane. Alright, so this is force by the spring and force by the plane. Now let's invoke Newton's third law of motion. What that law tells you, that F by the spring the magnitude of it is same as F by the plane. The magnitude, Newton's third law of motion. And there is another variable, that is delta L in the downward direction. So let me draw this on a XY diagram. This is my y-axis, this is my x-axis, this is my y-axis, and let me draw all three variables, all three vectors. So we saw, let me scale up, go up a little, that the plane experienced the force by the spring in upward direction. So this is force by the spring. This is my number one. Then I draw force by the plane. I can also call it or on the spring. And then let me also draw the compression, delta L. So delta L is also in the downward direction. So we have three vectors here: force by the spring on the plane, force by the plane on the spring, and the deformation delta L. Now Hooke's law states force is equal to minus K delta L. So F is a vector, K is a constant. This is your spring constant, and this is the deformation Now, why do we have delta L here with the negative direction, negative, this? So now you look at it here and see which one has opposite direction. So delta L and force by the plane on the spring, they're both downwards, and force by the spring is upwards. So you see here that this negative sign tells you that F by the spring is equal to minus K multiplied with delta L. So this I hope is clear, the point that we were driving, that Hooke's law E here. Hooke's law, when it says force is minus K multiplied with displacement, they're talking about force by the spring. So if I were to write down force by the plane on the spring, so force by the plane on the spring is in the negative direction of force by the spring. So if I wanted to write another version of Hooke's law, force by the plane is equal to plus K delta L. Why? As you can see here, force by the plane and delta L are in the same direction, and if I wanted to be really picky about directions, so force by the plane is minus, because it is in the negative direction, is equal to K multiplied with minus delta L, because deformation happened in the downward direction, minus Y direction. So again, this F is equal to K delta L. So it's very important to understand that Hooke's law is from the perspective of the body that the spring is working on. Now let's take another scenario. Of expansion. So this is a wall or support, and there's a spring laying here, there's a mass attached to it, and a force F applies in this direction, and that leads to extension. So I'm going to choose the color blue. So this leads to expansion. So this leads to the spring getting extended a lot, and this was original length was L, and this is L plus delta L. So imagine that this is the So let's look at the perspective of the spring. So spring is feeling a force in this direction, and the block is feeling a force in this direction. So let me call it F external, and this is F by the spring. And let me draw on axis the vectors. So this is my x, this is my y, and all vectors now are in x plus x or minus direction. So spring is feeling a force in this direction, which is F external. So let me do that in blue color. So this is F external. Delta L is also in plus x direction. So this is delta L, and F by the spring is in this direction. So let me, this is F by the spring. So now you see here that F by the spring is equal to K and multiplied with minus L, delta L. Why? Because delta L is in this direction and force by the spring is in the opposite direction. So that's why, again, Hooke's law will make it F is equal to minus K multiplied with delta L. So spring always resists deformation, whether it's expansion or compression. That's why this minus K delta L. Now the last topic of springs, energy. So you know this formula, that work is half k delta L square. Now we know from Hooke's law that F is minus k delta L. So when we have a spring like this attached to mass and there's a force in this direction, so as we saw before that F minus k delta L tells you that it is by the spring. So work done by the spring will be minus half k delta L square, and work done on the spring is plus half k delta L square. So it should be very clear from the video we saw before that how this plus and minus is happening. So let's go back to our favorite video. So this is right before the wheels touch the runway, and this is the body of the plane. So at this point, because of the weight of the plane, the compression will happen like this. Right? So delta L is also in this direction, but spring is applying a force by the spring. So spring is applying a force in this direction. So the work done by the plane, because of this force being in the same direction as delta L, is positive. Work done by the spring is negative. Now, why work done by spring is written like this, and where does the negative work go? So let me address the second part first. I have a spring attached to this mass, and the extension is delta L, and there was a force delta F. I am showing it in the wrong direction, so I have a force in this direction. So you'll say, oh, this is simple. This force is equal to K delta L. Now what happens if you remove this force? So let me use an eraser that you remove this force. What does your intuition tell you? So intuition tells you the spring will pull this mass in this direction. So that's your intuition. Let me write it so that you have this in focus. When you release the force, so let's draw the free body diagram of the spring and the mass after the force has been released. So this is the spring, and it is extended. So spring is extended, and it will apply a force in this direction. And the body will feel a force in this direction. So now you see the force by the spring and delta L are in the same direction. Similarly, if a spring is compressed, by minus delta L, and there's a force that keeping it compressed, when the force is released, spring will push in this direction to cover this deformation. So in this case, spring acts like a battery. There's energy stored in it. And what is that energy? So energy stored in this spring is equal to work done on the spring. Which is equal to work done by the spring when the force is released. I should say force on the spring. Is released. So energy stored in the spring is potential energy, is equal to work done on the spring, which is half K delta L square, where K is the spring constant, which is equal to work done by the spring when the force is released. So now let's work on how we get to this expression. So let me draw a diagram. So this is force, this is delta L, and we are taking the force by the spring. So Hooke's law is F minus K delta L. So if you see here, this is minus KL. So the force will go like this. And this is the case of when delta L is positive. When delta L is negative, in this direction, the force will be in the upward directions. Okay. So we want to calculate the work done by the spring in this area, and this is positive and this is negative. Now Hooke's law is minus K and delta L. So when, suppose you choose a point, let me use a different color. You are at a point X. What will be the force at this point? So force X is minus K X, and this is what makes it a challenge, because spring force is not constant, it's changing by X. So as you're moving, the force is getting in magnitude bigger and bigger and bigger, and over here at this point the force is minus K delta L. So there are two ways to solve it. One is with calculus or without calculus. So with calculus is more elegant, but if you are not studying for engineering or engineering entrance exam, you may not want, be interested in this. So this calculus way is that just imagine that I take a small slice and I call that dx. So work done is force and dot product of displacement. And in this case, force is minus kx and displacement is delta x. So in this small slice, and let's call it dw, the work done is minus kx multiplied with delta x, and if this is very small, we can also write it as minus k x dx. And we integrate it 0 to delta L. We integrate this side minus k x dx 0 to delta L. So this gives you half k x square 0 to delta L, and this becomes half k delta L square minus half k 0 square, which is half k delta L square. Now let's work on the second method without calculus. So because it is linear, we can say the average force is somewhere here. This is 0 here, and at this point the force is minus k delta L. So force average is minus k delta L minus 0 divided by 2. So you get minus half k delta L. So work is minus half force average multiplied with total displacement. So this becomes half k delta L square. So we found that how energy of inner spring or work done by spring, the formula work is half k delta L square, and if we want to see work by the spring, then we put a minus here. So that is all. This is the end. This is the end, and let's do a recap of all the 3 parts. We had a long journey here. We started with the topics that we will cover. In part 1 you have introduction, and in part 2 we went through prerequisites, very important, and in part 3 we applied the prerequisite knowledge onto a Spring. So thank you. Our session will start on April 1st. We are conducting admission tests at this time, and if you have any question, visit this website and leave a question or contact us. Good luck in your journey to become a doctor or engineer.